All right, good afternoon. Welcome to day 5 of our logarithm and exponential equation unit. Today we are going to do applications with logs. So yesterday we talked about how to graph log and exponential equations. Now today we are going to do a few word problems with them. So I'll walk you through that. We'll talk about exponential growth. We'll talk about half-life, a few other things, and get you rolling. So our exponential growth, that's when your rate is larger than 1. Exponential decay is where the rate is less than 1. So obviously if you're growing by 7%, for say that'd be 1.07, where if you're decreasing by 7%, it'd be 0.93, which would be less than 1. All right, our general exponential equation is right here. A is our amount. So this is our simple interest formula. P is our principal, or the initial amount, a rate divided by the number of times interest is calculated, and T is our years. Remember your rate as a decimal. If it's 7% is 0.07. If it was 5.5%, 0.055. So that'll come in handy as we go. So here we have a city population. Instead of money, we're dealing with population of people, 22,750 people, growing at 7.5% each year for 10 years. So we add our rate to 1. This is an annual rate, so we don't have to divide it by anything for 10 years. Remember, 7.5% is a decimal as 0.075. And so if we had this small town growing at 7.5%, it would more than double in 10 years, and it would have 46,889 people. All right, here's a more traditional financial example here. And so we have Sabrina, who is investing money. We want to know if she wants to have $9,000 after 10 years, and she has a quarterly interest rate of 6%, how much should she invest to begin with? So this is our final amount. We do not have the starting amount. 6% quarterly, so 4 times a year. For 10 years will be to the 40th power. So we figure out this decimal here, 1.015 to the 40th. I'm going to divide 9,000 by that number. And so when we do that in the calculator, she would have to start with a little bit under $5,000, $4,961.36. As we're going through this, feel free to hit pause anytime if you need to get caught up or finish writing something down. So I may be talking a little bit faster than you're writing. So again, hit the pause button anytime you need to. We can also use logs to find exact answers to exponential equations. So that's what our next few slides are going to deal with here today. So how many years will it take a $700 investment at 12% to compound to an amount of $47,000? So again, we start with a relatively small investment of $700. It's growing at 12% per year. We don't know how long it's going to be before that is $47,000. First step, we're going to divide by 700. And now I get this exponential equation, and I am going to take the log of both sides. So the log of 67.14 will equal the log of 1.12. Ultimately, what I'm going to have to do here is divide. So when I divide those two logs, it's going to take 37 years. Now, clearly, if this person invested more money along the way over the 37 years, they'll have more than 47,000. But if they just did it one time, $700, let it sit there at 12%, in 37 years, they would have $47,000. Okay, $2,500 investment in an account that compounds quarterly, so that's 4 times per year. And they want that to sit in there for 10 years. So 10 years times 4 is 40 times interest to be calculated, and they want that to double in that time. So if we started with 2,500, we're going to double to 5,000. If we divide that real quick, you see we get 2 here, which is no surprise because we doubled it. Need to get rid of this exponent. So to do that, I'm going to take both sides to the 1/40th power. That'll give me 1 plus r over 4 here. 2 to the 1/40th, we'll mess with that later. That's going to be a real tiny number. We're going to subtract 1 from that. And then ultimately, we are going to divide by 4. So 2 to the 1/40th power minus 1, multiply that by 4, and we will get 0.069 or 6.9%. So if you are investing with quarterly interest and you want $2,500 to double to $5,000 in 10 years, you need roughly a 7% interest rate. All right, number 9, E. coli bacteria can increase exponentially, so it doubles every 15 minutes. So, if you had 20 cells in 15 minutes, you'll have 40, and in a half hour, you'll have 80, and so forth. So we have a sample containing 1,000 bacteria. We want to know how long it's going to take before we have 64,000. So this is a continuous situation, and they gave us the doubling time. And so what we can do with that, we know that our time here is 15 minutes or 0.25 hours. So doubling time, you can take the natural log of 2 divided by your growth constant. Well, we don't have the growth constant, but we do have the time. So we are going to flip this around and solve for k. And so if I take the natural log of 2 divided by my time, I will have my growth constant, which is 2.77 or 277%. So it's almost tripling at that rate. So we started with 1,000, and then this is our growth constant here. It's constant growth. That's why it's E. To get rid of E, we're going to take the natural log of both sides. So natural log of E is 1. So this natural log is going to equal 2.77t. And when I divide that, it's going to take 1.5 hours to go from 1,000 cells to 64,000. So that is a pretty fast growth rate. That is why when they find E. coli in a sewer system or water system, they will shut it down. A couple of years ago, that happened in the Cudahy, Greendale, Glendale area, or not Greendale, Greenfield area. So they had to shut down the water to those towns temporarily to clean it out, obviously, because you don't want to be sending E. coli to all your houses. Pleasant thought on that, I know. All right, last one. Radon has a half-life of 3.82 days. So what that means is if you start with a certain amount, half of it is going to be gone after 3.82 days. So a house basement contained 32 grams of radon gas when the family moved in. If the source of gas is removed, then the radon eventually decays. And again, that's every 3.82 days. How long will it take until there's only 6.2 grams left? So we know it'll go from 32 to 16 in 3.82 days, from 16 to 8 in 7.64 days, but we want to get down to 6.2. So we know we have half of what we started with, so half of 32. We want to get down to 6.2 grams. So we are going to find our time here. So we divide by 32, take the log of both sides. And what T gives us in this context is the number of half-lives. So our T right here is 2.365 half-lives. And we have to multiply that by the number of days in the half-life. And our problem told us that that was 3.82 right up here. So 3.82 times the number of half-lives, it is a little bit over 9 days. Will get us from 32 grams of radon to 6.2. Not that you would know this, but radon is very common in basements in southeastern Wisconsin because of the heavy clay soil. So that's one of the things they test for when they buy and sell homes, to make sure the radon levels are not too high. So again, that's common practice in southeastern Wisconsin given the soil base that we have here. So that's a handful of examples with applications of logarithmic functions that will prepare you for our Day 5 worksheet. You've got the duration of the hour to work on that, and we will see you on Monday. Thanks.